Because the maximum specific growth rate of nitrifying organisms is so important in order to establish nitrification in the activated sludge system, we give this maximum specific growth rate a factor of safety. It's really an uncertainty factor in order to ensure that the system nitrifies. And this factor of safety has a symbol S subscript F, and it is a number that we would choose depending on how uncertain we are about the maximum specific growth rate. The more certain we are about it, the smaller the factor of safety we could give it. If we're not very certain of the value, then we would have to give it a higher factor of safety. Now, this factor of safety ensures that the sludge age of the activated sludge system is larger than the minimum for nitrification in order to ensure that the system nitrifies. It covers our uncertainty in this maximum specific growth rate of nitrifiers, and it also ensures that the effluent ammonia concentration is very low and that nitrification is near complete. You may recall from that graph I showed earlier that as the sludge age begins to approach the minimum for nitrification, the effluent ammonia begins to increase. And so this factor of safety also pushes the sludge age of the system away from the minimum for nitrification, making sure that the effluent ammonia concentration is low. And if we establish the sludge age of the system at that value which we have a certain factor of safety, then the effluent ammonia concentration is very simply given by the half saturation coefficient divided by the factor of safety minus 1. So, if the sludge age of the system is far away from the minimum from nitrification, then the mu value is overly large, in the sense then our factor of safety will be high. And with a high factor of safety, minus 1, we'll end up with a low effluent ammonia concentration. If the sludge age of the system is close to the minimum sludge age for nitrification, the factor of safety that we have on the mu value will be low, let's say 1.3, then the effluent ammonia concentration will be 1.3 minus 1, which is 0.3, and it will be the half saturation coefficient divided by 0.3. And if the half saturation coefficient is, say, 1 milligram per liter, then 1 divided by 0.3 is 3 milligrams per liter of ammonia. And so this equation applies for a defined factor of safety. The larger this factor of safety, the longer the sludge age away from the minimum for nitrification, the lower the effluent ammonia concentration. Now, the factors that affect the nitrification process. We have already discussed that this wastewater composition may influence the maximum specific growth rate of the nitrifiers. We may have all sorts of metals and inhibitors in the influent wastewater, and so the wastewater defines this maximum specific growth rate. Because temperature influences the maximum specific growth rate, we have to define the maximum specific growth rate at a certain temperature. We select 20 degrees centigrade as our datum, and we specify the maximum specific growth rate at 20 degrees centigrade, and then would calculate what it would be at 14 degrees centigrade or 22 degrees centigrade, depending on the temperature that you wish to design the activated sludge system for. Now, so temperature influences the maximum specific growth rate, and we're going to look at the equations that are used to calculate maximum specific growth rates at different temperatures when we know the value at 20 degrees centigrade. Unaerated zones influence the maximum specific growth rate, and we're going to examine that. The aerobic reactor dissolved oxygen concentration influences the maximum specific growth rate, cyclic flow and low conditions, and also the reactor pH. And we're going to examine each of these 6 influences on the maximum specific growth rate All right, so as already mentioned, the maximum specific growth rate varies much between different wastewaters, and so is a wastewater characteristic rather than a kinetic constant. Ideally, it should be measured on the wastewater. MUNIM 20 values have ranged in the literature between 0.3 and 0.75, and the endogenous respiration rate is accepted to stay constant at 0.04. And so the maximum specific growth rate is interpreted in terms of a fixed endogenous respiration rate, which we do not change. Temperature. The nitrifier kinetic constants, maximum specific growth rate, endogenous respiration rate, and half saturation coefficient all decrease with temperature. And the temperature relationships that we use are as follows. The maximum specific growth rate at some temperature T is equal to the defined value at 20, theta to the power of T minus 20, where this theta value is specific for a specific bioprocess. And in our case, the theta value for the maximum specific growth rate is 1.123. This is 12% change per degree centigrade. It's quite strongly sensitive to temperature. The half saturation coefficient also decreases with decrease in temperature at the same rate, 12.3% per degree centigrade. The endogenous respiration rate, on the other hand, is very insensitive to temperature, only 2.9% per degree centigrade. The same as the ordinary heterotrophic organisms which mediate the organic material removal. So this theta value, or temperature sensitivity coefficient, of 1.123 is equivalent to a 50% reduction in maximum specific growth rate every 6 degrees decrease in temperature. So if at 20 degrees centigrade we have 0.45 per day, then at 14 degrees centigrade we would have 0.23. That means that if the wastewater temperature is 14 degrees centigrade, the sludge age at 14 degrees centigrade would have to be double that at 20 degrees centigrade, because we've halved the maximum specific growth rate. Temperature, again, so halving the maximum specific growth rate at 6 degrees centigrade decrease doubles the minimum sludge age for nitrification. Halving the half saturation coefficient through a 6 degrees centigrade decrease does not affect the minimum sludge age for nitrification, but it does affect the effluent ammonia concentration. The overall effect of temperature on the maximum specific growth rate and the half saturation coefficient together is that the effluent ammonia concentration increases with a temperature decrease. So the lower the temperature, the higher the effluent ammonia concentration from the activated sludge reactor for a defined maximum specific growth rate at 20 degrees centigrade. Now, unaerated zones. How do these zones that are not aerated influence the nitrifying organisms? Remember, I mentioned nitrifying organisms are obligate aerobes. They have to have oxygen in order to grow. If they do not have oxygen, they do not grow. So, point number one is the autotrophic nitrifying organisms can only grow in the aerated zones of the activated sludge reactor. Secondly, the autotrophic nitrifying organisms do their endogenous respiration process in all the zones of the activated sludge process at the same rate. Now, this is somewhat controversial. People in the literature have argued about this, saying, no, the endogenous respiration rate in the unaerated zones is 0, or the endogenous respiration rate should be higher than in the aerobic zone. We've assumed, and that assumption is made in the activated sludge models as well, that the endogenous respiration rate occurs in all the zones, but at the same rate as in the aerobic zone. So we have endogenous respiration or mass loss of nitrifiers in the entire activated sludge system, but only growth happens in the aerobic zone. And then the third assumption that we make is that the autotrophic nitrifying organisms are uniformly distributed throughout the activated sludge reactor and have the same proportion of the volatile solids, whether they are in the anaerobic zone, in the anoxic zone, or in the aerated zone. So if I have, for example, 4% of my volatile solids is nitrifiers, then that 4% would apply to all the zones in the activated sludge reactor. The volatile solids concentration may be different in the different zones, but the nitrifiers are a constant proportion of that volatile solids concentration. That means that the nitrifiers are equally uniformly distributed around the wastewater treatment plant as the ordinary heterotrophic organisms. This is also somewhat controversial, but we make that assumption because the simulation models seem to indicate that that is a reasonable assumption, and the experimental behavior of the nitrification process also indicates that those are reasonable assumptions to make. Now, when we make these assumptions, the important implication of this assumption number 3 is that the sludge mass fractions of the different zones reflect the distribution of the nitrifiers within the activated sludge system. Let me explain what I mean by sludge mass fraction. Let's say I have 20% of my activated sludge in the whole of the biological reactor sitting in an anoxic reactor in an unaerated way to do denitrification. Then the anoxic mass fraction is 0.2 or 20%. On the other hand, if I have, for example, a biological nitrogen and phosphorus removal system, and I have an anaerobic reactor which contains 20% of the mass of sludge in the system, and an anoxic reactor which contains 30% of the mass of sludge in the system, then the aerobic reactor must contain the remaining 50% of the mass of sludge in the system. The anaerobic mass fraction then is 0.2. The anoxic mass fraction then is 0.3. And the aerobic mass fraction is 0.5. The unaerated mass fraction is 0.5 because 50% of the sludge in the system is not in an aerated form. But the other 50% is in the aerated zone. So when we say, this point number 3, that the proportion of the autotrophic nitrifying organisms is distributed in the same way as the volatile solids of the ordinary heterotrophic organisms in the different zones, then we can say that the sludge mass fractions apply also to the nitrifying organisms. And when we do that, we can show that the maximum specific growth rate of the nitrifying organisms in a way gets corrected by the unaerated sludge mass fraction. So this equation now applies for the effluent ammonia concentration when there is growth only in the aerobic zones, but if there is endogenous respiration in all the zones. And so you can see here that the endogenous respiration rate is in this equation together with the sludge age, but the maximum specific growth rate gets corrected for the aerobic sludge mass fraction, because FXT is the non-aerated sludge mass fraction of the system, and 1 minus FXT is the aerated sludge mass fraction. And so you can see that this part of the equation takes into account that there is only growth in the aerobic zone of the system. It has the effect of reducing the maximum specific growth rate of the nitrifiers, in effect. Well, because it can only grow in 50% of the process if 50% of the process is in an aerated sludge mass fraction. If we then, again, as previously, set the influent ammonia concentration equal to the effluent here, and we set the sludge age equal to the minimum sludge age for nitrification, and we solve for this unaerated sludge mass fraction, or alternatively for the minimum sludge age for nitrification, we find now that for activated sludge reactors which have unaerated zones, the minimum sludge age for nitrification is given as 1 upon the maximum specific growth rate of nitrifiers corrected for the unaerated mass fraction minus the endogenous respiration rate. So if we then make a graph of the maximum unaerated sludge mass fraction that a system would be allowed at a defined sludge age for a given maximum specific growth rate and endogenous respiration rate, and an established factor of safety for nitrification, and we plot the graph, we get a graph that looks like this graph shown here. On the horizontal axis we have sludge age, and on the vertical axis we have the maximum amount of sludge that can be in an unaerated condition in order to ensure that we get nitrification at that factor of safety. In this particular graph, the temperature is 14 degrees centigrade, and the factor of safety for nitrification is 1.25. Now, if the maximum specific growth rate of nitrifiers is 0.25, then if my sludge age is 20 days and the maximum specific growth rate 0.25, I am only allowed to have 20% of the mass of sludge in the system in an unaerated condition. If I have more than that, nitrification will not take place. If the maximum specific growth rate is higher, let's say it is 0.4 at 20 degrees centigrade, and my sludge age of the system is 20 days, then for a maximum specific growth rate of 0.4, I'm allowed to have 43% of the sludge mass in the system in an unaerated condition and still guarantee nitrification with a factor of safety of 1.25. So you can see from this kind of graphical behavior here that the higher the maximum specific growth rate, the larger can be the unaerated sludge mass fraction for a specific sludge age and still get nitrification. It is this reason that makes the maximum specific growth rate such a fundamentally important parameter. It will dictate the sludge age for which we must design this nitrogen removal system. Because, of course, if I want to remove a lot of nitrogen, get a high degree of denitrification, I would have to put a large amount of the sludge mass in a non-aerated condition. But I would still have to guarantee nitrification. That forces the sludge age of the system to be long. And that you can see from this particular diagram. If the maximum specific growth rate of the nitrifiers is very high, like 0.5, then if I had 15 days sludge age, I can have half or 50% of the sludge mass in an unaerated fraction and still get nitrification. Now, when the system is designed and the maximum specific growth rate and unaerated sludge mass fraction lie on the particular lines, then the effluent ammonia concentration is still given by Kn, half saturation coefficient, divided by safety factor minus 1. But if I should have a situation where my maximum specific growth rate of the nitrifier is 0.5 the unaerated mass fraction of the system is 0.4, and the sludge age is 20 days, then I fall in the diagram at about that position on the graph, which is far from the 0.5 maximum specific growth rate. When that happens, the factor of safety is in fact much larger than the 1.25 defined for this graph. Then the effluent ammonia concentration will be much lower. So the equation here, Na equal to KNT over SF minus 1, applies only for situations where maximum specific growth rate, unaerated sludge mass fraction, and sludge age fall on the line. If they fall outside of the line, the effluent ammonia concentration will be lower. If they fall to the right-hand side of the line, on the other hand, if it falls to the left-hand side of the line, the effluent concentration will be higher, and in fact, nitrification may in fact not take place at all. The fourth factor that we described as influencing the maximum specific growth rate is formulated in the normal monod kinetic way. So the maximum specific growth rate at some dissolved oxygen concentration of O is equal to the maximum specific growth rate at, let's say, 0.45, whatever the value may be, and then it gets multiplied by the dissolved oxygen concentration divided by a half saturation coefficient for dissolved oxygen plus the dissolved oxygen concentration. This is a monod a correction term for dissolved oxygen. Now, the important thing is the significance of this monod correction term would depend entirely on the half saturation concentration for dissolved oxygen. And in the literature, the value varies between 0.3 and about 2 milligrams per liter. And the reason why it varies depends on the flock size of the activated sludge in which the nitrification process happens. If the flocks are very small, dissolved oxygen can penetrate right to the center of the activated sludge flock, in which case you do not need strong dissolved oxygen concentration gradients into the activated sludge flock. In that case, the half saturation coefficient will be low. If the flock size of the activated sludge is large, now the dissolved oxygen concentration needs to be high in the bulk liquid in order to penetrate right through to the center of the sludge flock. Then we would have to have a high half saturation coefficient in order to model the effect of dissolved oxygen concentration on nitrification. But if the reactor concentration is less than this half saturation coefficient for dissolved oxygen, then the nitrification rate is less than half the maximum. And the implication of that is a doubling of the sludge age again, because the minimum sludge age for nitrification again doubles, because we've reduced the maximum specific growth rate now by restricting the dissolved oxygen concentration to a very low value. Generally speaking, it's best to have dissolved oxygen concentrations in the order between 1 and 2 milligrams per liter in the reactor to allow nitrification to proceed without undue resistance due to dissolved oxygen limitation. Now, the next thing that we've defined as influencing the effluent ammonia concentration is cyclic flow and load conditions. Remember, the free and saline ammonia concentration is a dissolved constituent. It is entirely dependent on the hydraulic retention time of the reactor, in the sense that if the hydraulic retention time of the reactor is too short, then the ammonia concentration will not be completely nitrified, and that ammonia concentration will run out with the effluent of the plant. It is the nitrification process that governs the sludge age of the system. Generally, the longer the sludge age of the activated sludge process, the longer the hydraulic retention time also. But cyclic flow and load conditions bring a high influent flow rate and a high ammonia load simultaneously onto the biological reactor during the peak flow period of the day. The nitrifiers are therefore experiencing a diurnally varying ammonia load on the biological reactor. And at the time when the ammonia load is highest on the biological reactor, the nitrifiers have to work their fastest, and they may not be able to nitrify that complete ammonia load that arrives on the biological reactor. And it is from that sense that the average effluent ammonia concentration over a 24-hour period where the ammonia load varies diurnally, that average ammonia concentration is always greater than the steady-state effluent ammonia concentration, where the steady-state effluent ammonia concentration is defined when the ammonia load on the biological reactor is constant over a 24-hour period. And that's what we're trying to say here in this first statement. The average effluent ammonia concentration under cyclic flow and load is greater than the steady-state effluent ammonia concentration. So the nitrification efficiency decreases under cyclic flow and load compared with steady-state conditions. And the higher the variation in ammonia load from peak to average, the greater will be the effluent ammonia concentration and the lower the efficiency of nitrification. So cyclic flow and load has a similar effect on the system as decreasing the sludge age. Because as I decrease the sludge age, I move closer to the minimum sludge age for nitrification, pushing up the effluent ammonia concentration. Therefore, if I want to compensate for cyclic flow and load conditions of ammonia, I should increase the sludge age over the steady-state system sludge age. Then the ammonia concentration will again decrease. So cyclic flow and load always has a reduction in efficiency of nitrification. And the further the sludge age is away from the minimum, the smaller that reduction in efficiency becomes. So if my actual sludge age on the system is double that of the minimum for nitrification, I will have very little reduction in nitrification efficiency by virtue of the diurnal variation of influent flow and load from the ammonia. On the other hand, if I have a sludge age that is close to the minimum for nitrification, diurnal varying flow and load of ammonia will have a large influence on the effluent ammonia concentration. So we can increase the sludge age of the system to compensate for cyclic flow and load conditions and keep the effluent ammonia concentration low.